So redox titrations. So redox titration allows us to determine the concentration of an unknown substance. Okay, and that's what we know titrations to be, right? So we've done acid-base titrations. The whole idea of an acid-base titration is to get the concentration or the molarity of an acid. But in this situation here, we're going to get the concentration of a substance which is capable of oxidation or reduction. Now, the unknown is oxidized with an oxidizing agent. That oxidizing agent, so in other words, the chemical substance that will undergo reduction, pulling electrons off of something else, causing it to oxidize, well, that will be our titrant. That is that dark purple, okay, potassium permanganate solution that I was talking about. That's what we're going to use in tomorrow's lab. Two commonly used oxidizing agents are acidic permanganate. Now I said potassium permanganate, but the potassium is a spectator. And also dichromate ions. We don't use dichromate very often though because it's carcinogenic. So acidic permanganate undergoes the following half reaction. Now, this reaction is exactly the reaction that we see in our table. So our table, this is the reaction that is fourth from the top. So it's at a voltage of 1.51 volts. So because this right here, our permanganate, is so high on the left side of the table, that means it is a very strong oxidizing agent. It loves to pull electrons off of other substances, causing them to oxidize. So it has such a strong ability to reduce that it's able to cause many other substances to oxidize. As I said before, potassium ion is just a spectator. So for example, acidic permanganate can be reacted with iron 2 ion to find the concentration of iron 2 ion in a solution. So what I've done down below here is that I've shown the reduction reaction, okay, with permanganate ion. And then just below that, if we were to take iron 2 ion, we would find that on the right side of our table. Okay, now because this is a multivalent metal, okay, that means we can actually go from iron 2 to iron 3 if it oxidizes and loses an electron. Okay? Then we notice, okay, well, there's an imbalance in the electrons, so you know how this goes. So we're going to multiply everything through by 5. And that's going to give us the following as our overall redox reaction equation. Okay, that's going to be important when we do our titration calculations because all those coefficients, okay, that's going to help us to get the mole ratio for the stoichiometry that's involved in that calculation. So what we're going to be doing is that we're going to take some of that iron 2 ion. So in other words, we're going to take some of that. We're going to add that to an Erlenmeyer flask. We're going to cause it to oxidize, and we're going to do that by adding permanganate. So we're going to be adding that purple solution a drop at a time, okay, until we reach the equivalence point. And here's the thing, is that so long as there is iron 2 ion present, it will cause permanganate to undergo reduction. So in other words, permanganate gets converted to manganese ion. And that's the thing that I'm going to make reference to down here. It says that permanganate is purple, as we can see, and manganese ion, though, is colorless. Now, when permanganate is added from a burette to a solution containing iron 2 ion, it is immediately reduced to the colorless manganese ion, and the purple color is destroyed. Now, at the equivalence point, the last of the iron 2 ion is used up. So I'm saying that once we've reached the equivalence point, okay, all of this ion is gone. And now there is nothing to cause permanganate to be oxidized. So in other words, that reaction stops happening. So the next drop of permanganate does not react. So it does not undergo reduction, and the solution then becomes a light purple. So we're going to go from colorless to a very light purple, not a dark purple. Okay, very similar to what we saw in our acid-base titration. We went from colorless, okay, to a very light shade of purple if you did your titration correct. So therefore, the endpoint is shown by a change from colorless to light purple. And again, light is the key. Now, the moles of permanganate added are equal to 5 times the moles of iron destroyed. So if you look at the coefficients in that reaction equation, the ratio, okay, of permanganate to iron 2 is 1 to 5. So that's just going to go on our mole ratio, and now we can calculate the concentration of iron 2 ion. So, sample problem. 25 mils of a solution containing an unknown concentration of iron 2 ion is titrated with 17.52 milliliters of acidified 0.1 molar potassium permanganate. Okay, what is the concentration of iron 2 ion? So, first thing that I want to do is I'm going to write out my reaction equation. Now, it's the exact reaction that you see up above, but let's say I gave this to you on a test and I did not give you the equation. Here's how you'd put it together. So, we are talking about the reduction of permanganate. So, I think I have this written down somewhere. Hang on 1 second. Maybe I don't. Okay, so permanganate. So it reacts with 8 protons, 5 electrons to produce manganese ion and 4 water. I'm just going to center that a little bit here. Okay, so that is our first half reaction. The second half reaction involves the oxidation of iron 2 to iron 3 ion. So we find iron 2 on the right side of the table. We can't find it on the left side because if we're finding it on the left side, we're indicating that it's also undergoing reduction. We can't have 2 reduction reactions. So we're finding it on the right side where it oxidizes. Now when it oxidizes, it goes from iron 2 to iron 3 and an electron. So again, I find iron 2 on the right side of our table here where it oxidizes, and then I show it as an oxidation reaction. I reverse the reaction. Now I'm going to put these two together, but there is an imbalance in the electrons. So I'm going to take this second half reaction, multiply everything through by 5. Okay, now those electrons cancel. And then this will be our overall redox reaction. Oops. Okay, why do we need this? Well, that's going to help us in doing the stoichiometry. We need it for the mole ratio. So what we have here is that our starting molarity was 0.1 moles per liter. So the potassium permanganate was 0.1 moles per liter. That's a salt. When it dissociates, we get 0.1 moles per liter of permanganate. So same amount. And I'm going to multiply that by the volume that was required to reach the equivalence point. So 17.52 milliliters. If I were to multiply those together, I would now have the moles of permanganate, and then I want to go from the moles of permanganate to the moles of iron 2 ion, not iron 3, iron 2. So it is going to be, so my unknown, so 5 moles, iron 2, over my known, which is 1 mole of permanganate. So at this point now, I'm going to have the moles of iron 2 ion, and we want to convert that to molarity. So I'm going to divide by the volume. So the volume that we use in the sample, that was 25 milliliters converted to liters. I have to put something in my numerator, so I'll put the number 1. Okay, and if I calculate all of this, that will give me 0.3504. Ooh, I left an insane amount of space here, didn't I? Holy moly, what was I thinking?
You have nothing. You always have so much space on the.
That's right.
You have like this tiny little top there.
Okay. All right, so we talked about also dichromate as a possibility. Dichromate is also a very strong oxidizing agent. It's found actually quite high up on the left side of our table. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's 9th from the top on the left-hand side, dichromate. It's also acidified. So it's also commonly used, but its color change is not as distinct. So the orange dichromate changes gradually to a green chromium 3 solution. You might be thinking, okay, well, going from orange to green, isn't that a dramatic change? Well, it's kind of a greeny orange to an orangey green. So, question, why don't we use strong reducing agents as titrants? Why don't we use strong reducing agents as titrants? Okay, the answer is because most are solid metals. So you might be thinking, okay, well, why can't we just take something that is a strong reducing agent or something that oxidizes? Why can't we put that in the burette and cause something which is higher on the left side of the table to undergo reduction? Well, this is the reason. Most of them are solid metals. I cannot take lithium, cesium, rubidium, potassium, barium. I can't take any of those metals, stick them into a burette and add it to a solution and drop at a time. Okay, so this is why we are only able to do these types of redox reactions here. So we can cause the oxidation of iron 2 to iron 3, but we don't have a whole lot of options here. So, last thing here, and this just makes reference to a primary standard. Don't worry about this too much because it will not be on a test. And I think it's kind of confusing. We talked about this a little bit with acid-base titrations. So as in all titrations, the concentration of the titrant used in analysis must be accurately known. If the titrant is not a standard solution, so a solution of a precisely known concentration, it can be standardized by analysis with a primary standard. So let's say I wasn't able to accurately get the molarity of my potassium permanganate. Okay, well, I might use something called a primary standard to get its exact molarity. It says this is a chemical which is available in a pure form that is used to determine the precise concentration of a reagent, such as our permanganate over there. All right, so 2 practice problems. I think I'm going to have you work on both of these.